Hello everyone, welcome back to Physics-Based Animation. In the last video, we saw a little introduction to physics-based animation and learned a bit about variational mechanics. We ended by applying variational mechanics to a simple mass spring system, but we stopped with a bit of a cliffhanger. While we were able to derive Newton's second law for our spring, we never discussed how to actually generate an animation from it. This seems like a bit of an oversight for a course focused on animation. But wait no longer. We're going to address that missing piece of the puzzle today when we talk about time integration. But first, a little bit of review. Remember that a physical system's trajectory, its motion, can be represented by a curve parameterized by time. And this is all done in the space of generalized coordinates q. We always assume we have some additional function that will reconstruct the object's world space position from these q's. You can review this in the previous video. Newton's law, this second-order ordinary differential equation, is really just giving us some local information about the curvature of our trajectory in time. Time integration is going to take this local information and synthesize the full function q as a function of time. Generating a simulation or animation is then just traversing this curve in time. And as we can see, for every point in time we'll generate a q. Those q's will generate the position of these objects, and we generate an animation by computing all of these q's in sequence. Alright, we can think of time integration as a function or procedure that takes in a differential equation. And here I've hidden the mass inside of the right-hand side of the equation. Along with some initial conditions, information about where our object starts in the world and how fast it's going initially, and produces a discrete update equation, which tells us how to choose the next point on our curve. We will indicate the current point in time using a superscript t, and the next point in time using a superscript t plus 1. The time elapsed between t and t plus 1 will be denoted as delta t later in the lecture. Evaluating this update equation sequentially will produce a sequence of q's through time, and this will produce our simulated or animated result. Let's look at how to do this for our 1D mass spring system from the last video. We'll see in the next lecture that these concepts carry over to higher dimensions in a relatively straightforward manner. But for now, keeping it simple is going to let us work through the math and gain some useful intuition. So again, here's our mass spring particle setup with a spring attached to a wall at the origin of the space. We have a zero rest length spring attached to some particle with some mass. We're using the x position of this particle as our generalized coordinate and the velocity of the particle in one dimension as our generalized velocity. There are lots of approaches to performing discrete time integration. However, many apply to first-order differential equations rather than second-order differential equations. Motivated by this, we are going to transform our second-order ODE into a coupled system of first-order ODEs by introducing the auxiliary variable v, which is equal to the time derivative of q dot. Substituting this new equation into our second-order ODE gives us a coupled first-order system consisting of Newton's second law expressed using a single time derivative of the velocity and our equation relating v and q dot. For brevity's sake, it is often useful to express this equation in matrix notation. Here we introduce the 2x2 matrix A and the right-hand side term f, and most importantly, the 2D variable y. Y is the stacked vector of 1D velocity and generalized coordinate. A brief note. I realized that previously we defined v as the time derivative of the world space position, and I hope viewers will forgive me this overload of notation used to avoid introducing even more of the alphabet into the proceedings. Okay. So once rewritten in matrix notation, it really becomes clear that our second-order ODE, which featured the acceleration of q, has been replaced by a first-order ODE, just a single time derivative of y. 2D variable y is the time derivative of the 1D velocity and the 1D coordinate. 2D variable y is the time derivative of the 1D velocity and the 1D coordinate. 2D variable y is the time derivative of the 1D velocity and the 1D coordinate. 2D variable y is the time derivative of the 1D velocity and the 1D coordinate. 2D variable y is the time derivative of the 1D velocity and the 1D coordinate. 2D variable y is the time derivative of the 1D velocity and the 1D coordinate. 2D variable y is the time derivative of the 1D velocity and the 1D coordinate. 2D variable y is the time derivative of the 1D velocity and the 1D coordinate. 2D variable y is the time derivative of the 1D velocity and the 1D coordinate. 2D variable y is the time derivative of the 1D velocity and the 1D coordinate. 2D variable y is the time derivative of the 1D velocity and the 1D coordinate. 2D variable y is the time derivative of the 1D veloc We will be able to gain some insight into the motion of our 1D mass spring system by exploiting this new coupled system view of its dynamics. By definition, our new variable y is a 2D point. Its first coordinate is equal to the generalized velocity, and its second coordinate is q. Any point y can be plotted in a 2D space, which we call the phase space. The axes of the phase space are going to be our positional variable q and our velocity variable v. Now let's look at a single point in the phase space. This point has a positive q and a 0 velocity. Looking at our mass spring system, we can see that this corresponds to having a particle somewhere to the right of the origin, but with 0 velocity, so stopped at this moment in time. Our ordinary differential equation then shows us that the time derivative of v, the acceleration, will act in the negative x direction, and the velocity will be 0. Physical intuition tells us that this makes sense. Our spring should pull the particle back towards the origin, and we know from our initial conditions that the velocity at this point in time was in fact 0. And we can plot this vector in the phase space. We can go through the same exercise for a point in the phase space with q equals 0 and positive velocity. Physically, this corresponds to a point at the origin, but moving to the right. Here we see that our acceleration will be 0, the spring is not stretched, and velocity will be positive. And we can plot this vector as well. If we continue this exercise, we see that our differential equation specifies a vector field over the phase space. Remember that each of these vectors is the derivative of our phase space coordinate with respect to time. Our ODE tells us that any trajectory constructed via integration must be tangent to this vector field at every point. So if we pick an initial position and velocity, the integrated solution is the curve starting at this point and tangent to this vector field. For our mass spring system, we can see that such a curve is a closed circle. Again, physically, this all makes sense. There's no way for our spring system to lose energy, and so it should just keep vibrating with constant frequency and constant amplitude forever. While we were able to integrate this simple system by hand, more complicated differential equations are not going to be quite so friendly. To deal with this, we are going to turn to numerical rather than analytical integration schemes to trace these curves. When we talk about numerical algorithms for time integration, we generally divide them into two major categories, explicit and implicit. Explicit algorithms predict the next point in the trajectory using only information from the current step or previous to that in time. Implicit algorithms will compute the next step using information from beyond the current step. Now, I like to think of this as using information from the future. So what we're going to do next is to explore 4 popular time integration algorithms for physics-based animation. These are the algorithms that will allow you to actually generate animations from our second-order ODE, Newton's second law. When we consider the merits of each method, we're going to typically consider 3 things. First is the performance of the method, how efficient it is computationally. Second, we're going to consider the stability, and we're going to consider stability using the phase space. There are lots of ways to talk about stability for numerical time integration. Here we are going to focus on algorithm stability when applied to our fixed vibrating spring, and the phase space is going to be a useful tool to illustrate the concept. Given initial conditions, we know the analytical trajectory is a circle passing through this point. As we will see, a numerical integrator is going to trace out an approximation of this path in the phase space, and we would like this path to stay close to the analytical solution. If, for instance, the approximate path looks like this, our integrator will be unstable because q, the x position of the particle, is growing in an unbounded fashion. The particle is off to infinity and beyond, and this is going to generate some pretty funky animations. Finally, we care about the accuracy of our integrator. Now, the numerical methods literature has many definitions of accuracy, but in computer graphics we care primarily about visual accuracy. So for instance, in this fluid simulation, we don't care if this is following the trajectory that real fluids would. Rather, we care that it looks convincing and compelling. Okay, now, armed with our knowledge of the phase space and with some idea of what we want to look for, we can start discussing time integration. As usual, we will stick with our simple 1D mass spring model for now. To get going, we'll start with the simplest numerical time integration scheme. So famous, it even made a brief appearance in the hit movie Hidden Figures. That time integration scheme is called forward Euler time integration. Again, because we are focusing on a first-order ODE, we have only first derivatives with respect to time to consider. And so the first design choice we need to make is how to approximate this derivative. Let's make an easy choice. Let's approximate this derivative using a first-order finite difference. Here, delta t is the time elapsed between time t and time t plus 1. First order refers to the accuracy of this approximation, and you can learn more about this in any good textbook on numerical methods. You can see the course webpage for some of my own recommendations, and there's a link to this in the comments. We still have one more choice to make, and that is, where do we evaluate our function f? So again, let's make an easy choice. Let's evaluate it at the current time step. Now, a bit of rearranging is going to give us our update equation, where we see that y at t plus 1 is equal to y at t plus delta t A inverse f at yt. Finally, it can be convenient to expand this back into individual update equations for generalized velocity and position. Once we've done this, we can pretty easily see that this is an explicit method. Updates are computed using only information available at the current time step. We can also guess that this method is pretty efficient, needing only a single evaluation of f and a single inversion of our matrix A. We can't really do much better than that in this context. So what's the problem? Well, let's consider the stability of this method. Alright, here we are back in the phase space. Let's apply forward Euler integration to the initial position y at time equals 0, and we'll indicate this with the standard green circle. First, we compute our change in y using the forward Euler update equation, and then we can plot this as a vector in the phase space. Next, we update y to its new position at time equals delta t. Ideally, we want our discrete trajectory to follow the analytical trajectory of our system. But we can already see a problem developing. We can repeat this again for the next time step. We're already a bit off from the analytical trajectory starting at the first time step, but worse still, if we plot the analytical trajectory passing through our second computed configuration, we see that we're outside of that as well. In fact, this trend will continue for every time step we compute using our forward Euler time integrator. This means that our integrated trajectory will forever spiral outwards, away from the origin of the phase space. For elastic systems like our spring, this shows that forward Euler is completely unstable, meaning that despite its attractive simplicity, it's just not applicable to our use case here. So unfortunately, we are forced to turn to other approaches. Let's revisit forward Euler and see if we can come up with some ways to improve it. The cause of forward Euler's failure is that it integrates using an estimate of the slope of our trajectory, computed at the beginning of our time step. Maybe we can build a better slope estimate. Ideally, we would do this using only information from the current time step, keeping the method explicit for performance sake. Runge-Kutta time integration is a more advanced method that integrates using an average slope. To make this more clear, let's look at an example to get a feel for it. Rather than use a single slope for integration, we can use two. And that's going to give us an equation that looks like this. Don't be scared, there's a lot of things that are going to get introduced, and we're going to clear them all up one at a time. Really what this equation is telling us is that to make such an algorithm work, we have to make a few extra design choices. First, we're going to need to choose the times in the trajectory at which we compute these slopes. Second, we need to choose the coefficients for averaging the slopes together. And finally, in order to keep things explicit, we will estimate positions in the future, positions denoted by y superscript t plus a or y superscript t plus b, using our new friend forward Euler time integration. Note that here the time step t plus a is a times delta t units of time ahead of t. We complete the method specification by choosing the values of a, b, alpha, and beta so that our method gives us second-order accuracy in terms of local truncation error. If you're interested in learning more about things like local truncation error, again, I recommend any good book on numerical methods. So if we do this, it turns out we can show that a good choice of these coefficients is a equal to 0, b equal to 1, and alpha and beta both equal to 1/2. And if we plug these into our original update equation, we arrive at Hoyne's method, which is one type of Runge-Kutta integration scheme. Now, a reminder that this requires us to do an initial forward Euler step to evaluate y tilde, but that the method is still explicit as we don't need any information other than that which is available at time equals t. Typically, we rewrite such methods in a more compact form like this. Here it becomes clearer that we are only evaluating f twice to perform this integration, and we've introduced the variables kappa 1 and kappa 2 to store our slopes. This approach to building integrators is extremely flexible, and accuracy can be improved by averaging even more slopes and computing coefficients that minimize truncation error. One of the most well-loved Runge-Kutta methods in graphics is the fourth order variant, which is given by the following formula. Fourth order Runge-Kutta, or RK4 as it is commonly known, averages 4 slopes together to produce an extremely accurate time integration scheme. We can see that this method is still explicit and relatively efficient to evaluate, requiring just 4 evaluations of f. And, while sketching a phase-space picture is hard to do for this case, RK4 will prove to be much more stable when applied to our mass spring system. This really demonstrates the power of using simple integration schemes as building blocks of more powerful methods. But we aren't done there. In fact, now it's finally time to leave the land of the explicit time integrator and move on to one of the most, if not the most popular numerical integration scheme in computer graphics, the backward Euler scheme. The construction of backward Euler starts in the same way as forward Euler, with the replacement of our time derivative with a finite difference. However, while forward Euler evaluates f at our current time step, backward Euler will evaluate it at the next time step. Now, unlike Runge-Kutta methods, we aren't going to use forward Euler to estimate y at t plus 1. No, this is going to be a truly implicit integration scheme. In order to see how this works, we are going to need to revisit our ordinary differential equation. Alright, we've gone essentially all the way back to the beginning of this lecture, and we are reminded that the right-hand side, which I'd previously been denoting as sort of a generic function f of y, was actually linear in y. Let's make this linearity explicit by introducing the matrix B. And now we can revisit the backward Euler setup by taking this linearity into account. And continuing along, just as we did to drive forward Euler, eventually rearranging our equations to get a discrete update equation which computes y at t plus 1. But a problem has arisen. Y at t plus 1 appears on both sides of the equation. But fortunately, we can exploit the recently rediscovered linearity of our ODE to rearrange the equation further. By moving all the appropriate terms to the left-hand side, we can now solve for y at t plus 1 by inverting the matrix on the left. Okay, this is quite a complication to introduce, but let's use the phase space to see why we bother to do this at all. In order to understand what backward Euler time integration is doing in the phase space, we're going to have to unknot our equation a little bit. And what we can see is that backward Euler is relating the change in y between time steps to the slope of our differential equation computed at y at t plus 1, the end of the time step. Here we see where backward Euler gets its name. Forward Euler relates the change in y to the slope evaluated at the current time step, while backward Euler is doing the opposite. In other words, this integration scheme searches for a y at t plus 1, an updated position, for which this relationship will hold. Now let's look at this in the phase space. Okay, we're given a set of initial conditions, y at time equals 0, and we know that solving the backward Euler equation will compute y at t equals 1 such that we can recover y at t equals 0 by walking backwards along the gradient in phase space. If we compare this trajectory with the analytical phase space trajectory passing through our initial point, we see that the backward Euler step has fallen inside of the circle we expect. And of course we can take another step, and we see that the pattern continues. This next point falls inside the analytical trajectory, passing through the preceding configuration. This trend will continue, and eventually this phase space trajectory will spiral to the origin. At the origin, our particle is stationary at the wall. The system has reached a steady state, but all the energy has been lost. We call this loss of energy numerical damping, because it comes from the choice of time integration algorithm rather than something encoded in the equations of motion. While it may seem like a pathological error, this damping is very useful in computer graphics. First, it makes the integrator very stable. And second, almost all real-world objects demonstrate damping of some sort. And so the damping added by backward Euler can often serve to make animations look more realistic, more believable, without requiring additional modifications to the differential equation we're solving. I think this idea, and the fact that backward Euler is so popular in physics-based animation, speaks to the notion that we're really looking for visual plausibility rather than total accuracy in this field. Finally, as with forward Euler, it is useful to re-express the backward Euler update equation in terms of our generalized position q and generalized velocity v. Breaking our coupled first-order ODE into its individual equations gives us two update equations. Our goal is to disentangle them, which we can begin to do with a little rearranging of our position update. We can substitute the position update into our velocity equation, which gives us the following. Finally, rearranging the velocity update gives us two equations that we can solve one after the other to compute our backward Euler scheme. Okay, over the course of this lecture, we've developed two Euler integration schemes, and each one had issues, and we illustrated these issues by examining their phase space trajectories. Forward Euler was too energetic, it was too excited, and this led it to explode. Backward Euler was too low energy, leading to the introduction of artificial numerical damping. So wouldn't it be great if we could somehow combine these approaches to get something that was better than the sum of the parts? Well, that's the goal of our final time integration algorithm, which is called symplectic Euler. The idea behind symplectic Euler is incredibly elegant. Combine explicit and implicit integration steps to try and cancel out exploding and damping in order to conserve energetic behavior in some way. In particular, symplectic Euler updates system velocity explicitly in the same way as forward Euler, and then uses this updated velocity to, quote-unquote, implicitly update the position. Now, this isn't a full power implicit update like backward Euler. It's more akin to the RK4 style predictions used to improve integrator accuracy. However, in this case, we aren't improving the accuracy of the time integration scheme. Rather, we are making it symplectic. And symplectic is just a fancy word for area preserving. Let me show you what I mean. To do that, we're going to have to go back to our old friend the phase space and look at the phase space trajectory of this integrator. In fact, let's look at a single symplectic Euler update in the phase space. We can draw the triangle formed by y at time equals 0, y at time equals 1, and the origin of the phase space. And we can compute the area of this triangle. We can repeat this process, and if we do, we will find something interesting. The area of these two triangles will be the same. This is what symplectic integrators do by construction. Now note that for the more detail-oriented amongst you, you will notice that these triangles are not actually drawn with equal area, and so I'll freely admit that while symplectic Euler is area preserving in the phase space, my PowerPoint implementation is unfortunately not. Okay, let's draw a few more triangles. Again, these will all carve out equal area in the phase space. Because our triangles must have a finite area, no component of our simulation can go to infinity. This means that no matter how long we integrate our 1D mass spring system, the simulation will survive. And this is a very nice feature to have in an integrator. And with that, we come to the end of our whirlwind tour of numerical methods for time integration. In the next lecture, we're going to start taking all the things that we've learned and building fun simulations and animations in 3D. Thanks for watching.